Pluto is a far-off and baffling diminutive planet that was once an individual member of our planetary family. However, late frightening declarations by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They suggest that this frosty world is on a potential impact course with Neptune. But how might this occur, and what would be the consequences of such a massive event? Are we witnessing an interesting cosmic peculiarity, or is there something more to this impending grand collision? Join us as we explore the potential outcomes of a Pluto-Neptune impact. Pluto, a former planet that was downgraded to a dwarf planet partially because of its unconventional orbit, remains a subject of interest and study in the cosmic community. According to recent forecasts by leading researchers, Pluto's trajectory is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially dangerous impact between these two planets which could pose a colossal danger to Earth. How is such an event even conceivable? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a stunning 248 years to complete a single orbit. This means that since its discovery in 1930, it has yet to complete one full revolution. The intrigue doesn't stop there. Pluto's path is marked by its profoundly curved shape, veering significantly away from the nearly circular orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, calculated at 17 degrees to the ecliptic plane. The path Pluto follows is much more extreme compared to the other planets. This inclination and eccentric nature add layers of complexity to its orbital pattern. Quite possibly one of the most interesting aspects of Pluto's orbit is its intersection with Neptune's. For around 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we would expect from their positions in the solar system. This prompts the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to grasp its unique trajectory. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's path stood out with its steep inclination and elliptical shape. The mystery deepened with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of space mechanics. The three-body problem in space is about figuring out how three objects like Pluto, Neptune, and the Sun move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. For Pluto, this issue illustrates how its path, Neptune's orbit, and the Sun's gravity all work together in a complex manner. The terms alpha libration, scope libration, and the VZK oscillation are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. In relation to Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is situated about 90 degrees away from Neptune. This spatial separation is crucial in keeping their paths from impacting. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned significantly above their orbital plane, providing an extra layer of security from potential impacts. Another significant aspect of this situation is the VZK oscillation, named after three researchers, von Zippel-Kozai and Lidov, who studied how objects move in space. It describes how three space objects like Pluto, Neptune, and the Sun pull on one another with their gravity. This pulling influences their movements. In Pluto's case, the VZK oscillation helps us understand why its path around the Sun is so unusual. Despite Pluto's orbit appearing chaotic, this oscillation helps keep it moving smoothly over immense timescales. The VZK oscillation shows that even if things in space seem wild and irregular, patterns and rules still keep everything in balance. All of these factors help maintain Pluto's orbit, ensuring it doesn't collide with Neptune or veer off course. The three-body problem assists in understanding how these paths change based on how space objects pull on one another. Studying this helps us learn more about Pluto, our solar system, and even distant worlds orbiting other stars. Mathematical simulations in the late 1980s revealed that despite its stable properties, Pluto's orbit is actually turbulent. Minor deviations in initial conditions can lead to significant differences over thousands of years. Nevertheless, these unique properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping chaos in check. Recent computer simulations have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a special relationship with Pluto. For every 2 orbits Pluto makes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only planet at play. Jupiter's gravity also plays a huge role in safeguarding Pluto's orbit, and Saturn contributes significantly as well. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a stable path for billions of years. In a way, Neptune, Jupiter, and Saturn are working together to ensure Pluto continues moving securely in space without running into trouble. These celestial phenomena are fundamental to maintaining the order and stability of our solar system. Without these components, the solar system would be a place of much greater chaos and unpredictability. Bodies like Pluto could potentially crash into others or be catapulted from their stable orbits, leading to a cascading effect on other celestial bodies. For Pluto, particularly in discussions about a potential future collision with Neptune, understanding its orbit is crucial. This provides us with a clearer image of our solar system's dynamic nature. Pluto illustrates how even the most seemingly unstable orbits can achieve a state of harmony through the complex interplay of gravitational forces and orbital mechanics. Furthermore, Pluto serves as a crucial case study for understanding planetary formation and celestial dynamics. Scientists believe Pluto formed alongside other Kuiper belt objects in the early solar system. Studying its composition may provide insights into the conditions present during the solar system's infancy, potentially shedding light on the formation of Earth and other terrestrial planets. Recent research suggests that Pluto may have a subsurface ocean, a discovery that could change our understanding of its geology and potential for hosting life. Data from the New Horizons mission indicates that some areas of Pluto's surface, such as its icy mountains, may be composed of water ice which behaves uniquely under low temperatures. This revelation invites further investigation into the possibility of liquid water beneath Pluto's icy exterior, raising intriguing questions about the potential for life in extreme conditions. As more missions are planned, such as those targeting the far reaches of the Kuiper belt, we can expect new data that will challenge existing theories and expand our understanding of planetary science. Every discovery adds another piece to the puzzle of our solar system's history and evolution. Through these studies, Pluto remains a symbol of the relentless quest for knowledge about our universe, inviting both scientists and enthusiasts alike to ponder the mysteries that lie beyond our home planet. The future of Pluto exploration. Despite being reclassified as a dwarf planet, Pluto remains one of the most intriguing objects in the solar system. Scientists continue to study its complex geology, unusual atmosphere, and unique orbital mechanics, leading to new questions about its past, present, and future. While the New Horizons mission provided an unprecedented glimpse into Pluto's surface and atmospheric composition in 2015, many mysteries remain unsolved. One of the biggest questions revolves around Pluto's potential subsurface ocean. Evidence from New Horizons suggests that Pluto's crust may be covering a hidden ocean beneath its icy surface. If such an ocean exists, it could provide insights into the chemistry of extraterrestrial water bodies and even raise the possibility of microbial life in one of the coldest corners of the solar system. Future missions could send orbiters or landers capable of penetrating Pluto's icy crust to search for signs of liquid water. Potential missions to Pluto. Although no official missions to Pluto are currently planned, there are ongoing proposals for future exploration. Scientists and space agencies, including NASA, have discussed possibilities for sending another spacecraft to Pluto, this time with the capability to orbit the dwarf planet instead of just flying by. One such concept is the Pluto orbiter, which would use nuclear electric propulsion to slow down and enter orbit around Pluto. This mission could provide continuous observations of Pluto's surface changes, atmosphere, and moons, helping to unravel the mysteries left by New Horizons. Another ambitious idea is a Pluto lander or drill probe, which would analyze Pluto's icy surface and search for signs of subsurface liquid water. If successful, such a mission could revolutionize our understanding of Pluto's internal structure and its potential as a habitable environment. The Kuiper belt and beyond. Pluto is just one of many icy worlds residing in the Kuiper belt, a vast region beyond Neptune filled with dwarf planets, asteroids, and comets. Scientists believe that studying the Kuiper belt can reveal valuable information about the early solar system and how planetary systems form.